So for today's lesson, we're going to be doing something called dynamic programming. And this is going to be the last thing that we're going to be covering prior to, the CCC. And this is the last thing that I'll need you guys to prepare for. The last thing I'll prepare you guys for the CCC. And this would, and everything that I've covered so far, and including this, is all you need to solve all the problems in CCC Junior, and will help you get started in more advanced senior topics. All right. So if you recall from last week's lesson, this is one of the design paradigm algorithm design paradigms. If you need a quick refresher, here's a link, and there's a link to it. So if I open a preview, I talked about design paradigms, and dynamic programming is just pretty much just overlapping subproblems that solve a larger problem, I guess. Now we can restore later, and we can retrieve later to solve a bigger problem. So let me get started with introducing dynamic programming. All right. Now let's say I give you the following math program. It comprises just a list of ones, and I just tell you to add them up. So it's just here it's 10 ones. All right, and I say that equals 10. 1 plus 1 plus 1 plus 1, so on and so forth. That equals 10. Then let's say I just add a plus 1 to the end of the list. In this case, well, since it's kind of just a small number of ones, you could go in and just count the number of ones and just add them up. But let's say I gave you 100 ones, 1,000 ones, 1,000,000,000 ones. You would probably go through and count them. You probably wouldn't go through and count them. First you'd count them up to get all the sum, because you'd never did a sum before. But let's say I threw in an additional one at the end. You would not want to count that up. That's too much counting. You would probably just take the previous answer and just add 1 to it. And that forms the basic idea of dynamic programming, or shortened as DP. So to recap, DP is similar to divide and conquer, where you split up a large complex problem into smaller subproblems. But it differs, where DP consists of overlapping subproblems that can be stored and used later, and greatly improving efficiency in terms of time complexity, but coming at the cost of space efficiency. So going back to that previous, my example here, you had to store that previous answer in your brain, right? But then I throw in a 1. You already solved the previous answer, and that's the overlapping overlapping part. And there's the additional part where you just add 1. That's another subproblem. And you don't have to go back and count everything. That would have taken too much time. But that came at the cost of you having to memorize that previous answer. And that's the space efficiency. That's the cost of space efficiency with dynamic programming. So to split up a large problem into smaller subproblems, there are 2 thought processes that we need to dive into. So these are top down or bottom up. These also create 2 techniques that you will need to use for DP, called tabulation and memoization. And no, I did not spell memorization. It just doesn't include an R, so it's pronounced memoization. All right. So that's just the basic introduction. If anyone has questions about that, feel free to stop me, shout at me, or post in the chat. But let's go on to the thought process of splitting up a question, right? So there's top down or bottom up. So let's say we had to do some large tasks, such as being an amazing programmer. Now, you can't just instantly be an amazing programmer. If there was a secret to that, then I would have definitely taken that shortcut. But we need to split this task into smaller tasks that we can achieve. All right. So for a top-down approach, we would start from the bigger picture, then work our way down to the smaller details that we can easily work on. All right. So for this example, first I'm going to say I will be an amazing programmer. All right. And then someone will ask how, because that's a large feat to do. You have to split that into smaller tasks. I respond by saying I will work hard, in order to be an amazing programmer. And then someone will ask me, that's a large task to still do. How will I break that down? I will write, contest. That's still a large task to do. How will I do that? I will practice programming questions. And then someone asks me how will I do that? I will learn how to program and study, And that's something you can start. That's something small we can start with and build our way up to this large task of being an amazing programmer. Now, that's the top-down approach. That involved me breaking down this large task down to the smaller task. All right? For a bottom-up approach, we would start from the smallest picture, then work our way up to the largest picture that we're trying to solve. So it's starting with something small, and then we just gradually add to it to make something big. So for this example, first I will learn how to program. Then from learning how to program and study, I can write contests and practice programming questions. Then from practicing programming questions, I can take part in contests. Then from taking part in contests, I can work hard. I will work hard. Then from working hard, I will be an amazing programmer. This same idea of top-down versus bottom-up is very important for dynamic programming, as you will need to determine how you approach your question and how you will achieve your answer through subproblems. So now with dynamic programming, you'll need to store your subproblems answer somehow. And this gives us two techniques that I mentioned earlier. So first one is memoization. So memoization is a technique used to speed up your code by storing expensive function calls and returning the stored value when you need to call that function. So this is a top-down approach because when you split off into the smaller subproblems, you'll need to store the results of the subproblems for later use. And when you think of it, like those functions, I guess, like that's an expensive thing to do. That's a hard feat. And if I just store it for later use, I don't have to, go back and keep it's like splitting off into much more expensive function calls, I guess. Much more hard task to do. And this is opposed to tabulation, which tabulation is a technique where we directly solve the subproblems itself. And it's used in a bottom-up approach since we're solving the smaller problems first, rather than focusing on the bigger picture. And we keep calculating for the smaller values until we reach the bigger picture, and that's why it's a bottom-up approach, and it's called tabulation since we're calculating values in a table. Like when you think about it, it's values in a table. Solving like let's say we're doing like a parabola or whatever, and we're trying to find values, points on a points on a graph or whatever. You wouldn't just start by like scattering some values. No, you'd go probably into some order, I guess. And that's the same idea with tabulation. All right. So we can use a previous thing we've discussed earlier, which is the Fibonacci sequence. So in recursion lesson, I showed you the Fibonacci sequences in recursion. So if you need a refresher, I provided a link to it. And if you're unable to go to the link, there's the full link to that lesson. Now, if we look at the recursive calls for a Fibonacci function, you will see there are overlaps in the calls we make. So for fib at 6, you'd call fib at 4 and fib at 5. So fib at 5 would call fib at 4. And you'd see that's an overlap there. And fib at 4 calls fib at 3, but fib at 5 also calls fib at 3. And that's an overlap there. And so on and so forth, you can see some overlap in there. So rather than, and you can see it's calling those tasks again and splits down. And we're kind of just repeating things that we've done already. So rather than computing each function call every single time and wasting more time by, having to recalculate things, we can store the results of the calls and use them later to speed up our code. So let's start with the original code. So for a recursive function, we start with, we define the Fibonacci sequence. If the number is less than or equal to, we return 1. Since the Fibonacci sequence, it starts off with 1, 1, 2, 3, 5, so on and so forth. And the first two values of the Fibonacci sequence are just 1. And if it's not the first two values, then we just know, hey, add the previous two values. Simple. All right. Now we need to change this so that we can store answers once we calculate the answer. So let's add a dictionary that corresponds each Fibonacci number to the answer, I guess. So 1 is 1, 1, it's the Fibonacci sequence starts with 1, 1. So the first index of the Fibonacci sequence is 1. Second one is 1 as well. Now we go in and we check, okay, is it less than 2, and so on and so forth. If not, then return 1. Now, if we haven't found it yet, then we just say, okay, let's say at this index, we find a Fibonacci sequence. So fib at num minus 1 plus fib at num minus 2. All right, and we store it at the dictionary. And then we return that value since, once we found the answer, we return that value. Now, this only stores the values. We're not doing anything with the values yet. We're not checking if the value exists, and if so, then we return that value. But you have to do something with it. We don't. And let's say we get called a function again. In this code, nothing necessarily happens. We still run the fib at num minus 1 plus fib at num minus 2 because there's nothing stopping it. There's nothing stopping it from saying, oh, we've already found this before. So we have to check in our function whether or not we found the answer already. We already know the answer. And if we haven't, then we have to run the code. And if we have, we can just output the answer since we already know it. So first thing we do is we just check, hey, if the number exists, if we already know that, if we already found the answer in the memory, then we return it. And that's what we do. So we just go in and say, hey, okay, if it exists, return. And if not, it just proceeds with the normal code where we just check if it's less than 2, return 1. And if we haven't found it, I guess, then we just, we'd call fib num minus 1 plus fib num minus 2. All right. And this is an example of a top-down approach. Since we're still, breaking down the larger number into smaller components, I guess. All right. And then we use memoization here. So this is memoization, where we store, once we calculate the answer, we store it for later use. So if we haven't found it yet, then we calculate for the number. So fib at num minus 1 plus fib at num minus 2, where we store a number and return that number. But then let's say we need that number again. We just check, oh, we found the number. Great, return it, done. And that's memoization here. So that is, now, that's only the top-down approach. Let's say we want to work bottom-up, the opposite direction. Let's say from bottom, we start, at the very bottom and work our way up. So with the Fibonacci sequence, we're given 2 numbers at first, 1 and 1. What can we do with these 2 values? We can determine the next value, which is 2. Oh, we have 1, 1, 2 now. What can we do now with these numbers? We can determine the very next number. That's 3. We have 1, 1, 2, 3. What can we do with these numbers? Oh, we can determine the next value. 2 plus 3, that's 5. So on and so forth. We get 2, 3, 5, 8, 13, so on and so forth. And there you go. That's how we can determine any number in the Fibonacci sequence from the bottom up. And we can just code it. So we first start with the first 2 values of the sequence. That's 1 and 1. Now, we're trying to go to some random value n, all right? So since we already first know the first 2 values, we can just jump directly straight to the second value, I guess. The very next value after that, which is 2. Since we're 0 index, so it can't start with 0. Since we already know the 0th value, we already know the first value. We just jump directly to the second value. So in here, and it goes up until the very last number. And here we just add to the list the sum of the previous 2 numbers, since that's what the Fibonacci sequence is. And it'll just keep looping through and just adding the last 2 numbers and adding that to the list. And you can see that we worked our way up to the largest number using just the smaller numbers, but we already calculated before, stored them, and then we use them to calculate the larger numbers. And that's the Fibonacci sequence using dynamic programming. And that's much faster than what we were doing before with the recursion, where you can see it branches off. And here, we just do this in a straight line, I guess. But this comes at a cost. since, you can see that we're storing values here. All right. So now let's move on to the next thing of dynamic programming, and it's something called a prefix summary. So before that, does anyone have any questions about what I've just taught so far? All right, I'm guessing not. Let's move on to the prefix summary. So let's make a hypothetical here, and I'll just give you a list of numbers, and let's say the numbers is 1, 10, 2, 5, 8, 16, 24, 3, and 8. All right. Now I'll ask you to get the sum of the whole list. Simple. You would go through and just add them up, every single number. Now let's say I ask for the sum of the first 3 numbers. That also sounds simple. You just go in and add the first 3 numbers. Then I'll ask you to for a sum of the numbers between the third index and the 7th index. You'd probably start from the 3rd index and add every number up until the 7th index. But what if I give you a very large list of numbers and I ask you for multiple sums? Let's say, I ask you for the sum of the whole list. Then I ask you to sum for half of the list. I ask you to sum from the 2nd index to the 234th index or something like that. You'd probably be sitting here for a while if you use that same mentality of just going through and counting every single number. This is where prefix sum arrays come into play. So a prefix sum array is an array of integers that is just the sum of the prefixes, or simply as it's just a running total. So like a running total would be like you'd count 1, you add 10, so that'd be 11. You'd add 2, that'd be 13. You'd add 5, that's 18. So forth. That's a running total. And the prefix summary is just it keeps a running total of a given list. So let's go back to the hypothetical list before. So we create a prefix sum array by just keeping a running total of the list. So it'd go like this. So the first value of the prefix sum array would just be the first value of the list. Simple. The second value would just be the first value plus the second value. The third value of the index prefix sum array would be the first, second, third value, the sum of the first to third values, so on and so forth. So it'd be like 1 plus 10, 1 plus 10 plus 2, 1 plus 10 plus 2 plus 5, 1 plus 10 plus 2 plus 5 plus 8, and so on and so forth. So without any manipulation, this is pretty useful for just finding the running total from the start of the array to any given index. However, with a bit of math, we can find the sum of the numbers between any 2 given indices whatsoever. So if anyone hasn't taken any math or just doesn't remember about algebra, you may recall if you do something like if you have a plus b plus c plus d plus e minus a quantity a plus b plus c, you can you can see that there's an a minus a, there's a b minus b, and there's a c minus c, and those cancel out. That just leaves you with d plus e. And we can use the same principle of prefix sum arrays, where if we find the sum of an array, like let's from 0 to 8, and we subtract the sum of the array between 0 and 3, you'd just be left with the sum of the array between 4 and 8 to 8. And that's the same idea with prefix summary. And that's the whole gist of a prefix summary. It gets you the sum between any 2 given indices. So let's code out a prefix summary. So first, we need to actually be given an array. If we don't have an array, then we can't really make a prefix summary. That would not make any sense. Then you would need to create an array that will store a prefix sum array. There, the first index of the prefix sum array should exactly be the same as the first value in the given array, as you haven't really added anything except the first value. And then we can use dynamic programming here, where if you already know the sum up to a given point, the next value, if we just would just be the previous value plus the next number. Since why bother having to go through and count every single number again? If you already know the value up to, let's say we know the values between 0 to 3, and now we want to know the values between 0 to 4. If we already know the values between 0 to 3, we just need to add the 4th index, and now you get 0 to 4. Right? Simple. So let's code this up. So first, we create a prefix sum array, the array, and it's just 0 for the whole. We just create. It's the same size as the array we're given. So I just said for range len array, and I just started with 0. So it can be any number, but I'll just start with 0. All right. Now, the first value of the prefix sum array has to be the same as the given array. Now, we already calculated for the first value of the array. Let's go to the next number, which is 1, up until the end of the array, and we just say, hey, the value at the prefix sum array at a given index is just the previous number that we calculated before, So let's say 0 to 3, and now we're calculating for the 0 to 4, I guess. We just get the value from 0 to 3, and just add the fourth index, and you're done. And that's the same idea in this principle here. Now, let's say that constructs the prefix sum array. Now let's say we wanted the sum between the first index to the 8th index. What you do is you do prefix sum array at 8 minus prefix sum array at 0. You need to subtract 1 from the second value, since the value gives up, let's say, prefix sum array at 0 gives you the values from 0 to 0. Prefix sum array at 1 gives you the values from 0 to 1. And that's inclusive, so it includes 0 and at index 0. At 1, it includes 0, 1. Prefix sum array 2, it includes 0, 1, 2, and so on and so forth. Now, if we want every number beyond that, we'd have to subtract what comes before. So let's say we have values 0, 1, 2, 3, 4, 5, 6, 7, 8, and we only want values from, let's say, 2, 3, 4, 5, 6, 7, 8. You have to remove everything that we have to remove the 0, and we have to remove the 1. So we'd remove the first value, prefix sum array at 1, and we get 2, 3, 4, 5, 6, 7, 8. Does that make sense? So that's why we subtract 1 from what we're starting from. So we have the ending value, which is some right. So if we think from left to right, it's the last value, and then we subtract the first value, minus 1. All right, and that's a prefix sum array. So does anyone have questions about that? If not, all right, let's move on to difference arrays. So now let's say we're using the same hypothetical list from earlier. And let's say I ask you to increase numbers between index 1 and 5 by 10, or decrease numbers between 2 and 4 by 3. I'm guessing you would go through and add, subtract from the list one by one. Now, let's say I gave you a massive list. You would probably be here a while before you gave me the final answer. So, rather than making changes directly to the list, we can keep track of what changes we're making to the list, then apply them later once we actually need to find the values. So this is where difference arrays come in. They keep track of the difference between a given number in the list and, let's say, the previous number from the list. So let's say we increase the difference of a given number in a difference array. So every number, so let's say the difference between this first value and the second, and the next value is like 10. The next value, the difference is like negative 20, all right? So let's say we make one change in the difference array. Let's say we increase it by 10. Everything beyond that point, that change, will now correspond to what I changed that difference, I guess. It might be a bit confusing to explain, so let me just create like a whiteboard. It's like a domino effect where you make one change, everything else in the future gets affected. So let me just bring up whiteboard here. Oh, whoops. Create new, and let me just bring up my whiteboard here. So let's say we have the values like 10, 20, 5, 6, 8. Oh, whoops, that's going off my screen. 8, 9. All right. What's the difference between the 0 and 20? Do you just, oh, whoops, that likes to go off for some reason. All right. The difference between these two values, you just add, 10. Here you'd subtract 15. Here you'd add 1. Here you'd add 2. And here you add 1 again. All right. Now let's say we increase the difference of this. Let's say we have, instead of adding 10 now, we add 20. All right. So let's say we add 20 now. Here increase the difference by that number is now 30. But every other difference beyond that point is still going to be exactly the same. So, the difference between, we subtract 15 from now on. So if we subtract 15, that gives us a value of, is a number after 7, 8? Yeah, that should be 8. That should not be well, it's 6, then 8. So that should be an 8. So next value here, so after 10 would be 30. Right? But if every other difference is exactly the same, then they should have been affected by that increase. So subtract 15 from that would be 15, all right? And it's still affected by that 10 increase here from before. If we add like 10 here, right? You can see that's still affected by that increase. And every other value is also affected by that increase. So if we add 1, that's 16. If we add 2, that's 18. If we add 1, that's 19. And you can see every value now is added by 10 now. And that's the beauty of a difference array, You make one change, everything in the future will now be changed. So let's say, instead of, adding 2, let's say I would want, so instead of plus 2 between these two, let's say I wanted subtract 5, so minus 5, all right? 16 will now become 11 instead of 18, And now this next value will still be one difference away from this other value, so it'd be 12. 12 here. Or let's say the value you want just to go back down 10 10 numbers, I guess. So let's say we only wanted these 3 numbers to be increased by 10. So let's say instead of adding 2 anymore, we subtract 10 from that, so that would be minus 8. So we'd minus 8 from that. So this would give you back to 8. And the difference for the next value would be 9, since we still have to add 1. And that's the same idea with a difference array. So once we make one change in the difference array, every future value has a knock-on effect where it's now going to be increased by 10, it's going to decrease by 10, and so on and so forth. All right? So, and the same principle applies if we decrease the difference of a given number in a difference array, where every future value is now going to be increased or decreased by that value. So to construct a difference array, it's similar to a prefix array, but instead we're subtracting between the 2 numbers in the original array, since we're trying to find the difference between those 2 values, and like we're subtracting the difference between a number at a given index and a number previously before that index. So for the first number, we'd still give you the very first number in the prefix in the list. Like the prefix sum array. We also have to add one more value at the end of the difference array, as you would soon find out. I won't explain now, but we'll soon find out. So to code it up, so we start off with a difference array. I start with 0 for I in range len r plus 1. So we add one more additional value. All right. In a difference array, the first value is still the same, and you just loop through from 1 to the end of the difference array, and you just find the difference between each index and the previous number before it. So it would just be r1 minus r minus 1, and you set that at the difference array. Now let's say we wanted to update the values at a given index L and R by a given value of V. So we'd go into the difference array and increase the difference of index L. So that will increase every value past L. But that also goes past R as well. We have to, we're updating every value after L. So to counteract that, we also need to decrease the difference of everything past R plus 1. So this is where we're adding one more value in the difference array at the end, since it comes in handy if we want to update up to the last value. If we go past the array, it will give us the errors. But if we just add one other value, we can just change the last value and not care about any mistakes. All right. So the code here would be that should be a minus. So difference array at L would just you increase the value by v, and then difference array of r plus 1 would be minus v. Now this gives us a difference array, but we're not actually updating the array itself. We still need to get the original values of the difference array. So to do this, we just need to work backwards of creating the array when where we started with the starting value. Then we go back, then add back the values. It's exactly the same way as a prefix sum array. So we first set the first value of the array to the first value of the difference array, and then we just go in from the first value up to the end, and we just set the array at 1 equals the previous value plus whatever difference in the difference array. All right, and that's a difference array here. Does anyone have questions about that? I guess not. All right. So those were two, I guess, not necessarily the creation of those two previous the prefix sum array and difference array. Those use dynamic programming. However, we treat prefix sum arrays and difference arrays as data structures. So these are kind of just structures that we use to store data, I guess. But the creation of those is dynamic programming, since we're creating smaller problems to solve a much bigger problem, just in order to save some time. But now moving forward, we're going to be talking about some basic questions, dynamic programming questions that you will encounter when doing dynamic programming. And these are the questions that I will assign you for this week. No, I won't be covering the code, as they're going to be the questions for this week that I'll be assigning you guys, of course. I'm not letting you, you guys will have to, for dynamic programming, you will have to actually think about the questions that you're going to be writing and the answers. So if you haven't been doing the questions before, that's, I guess, I do encourage you guys to do the questions this week, since, dynamic programming is a kind of a thought process. There's a thought process behind it where you need a level of, like, I guess, intuition, I guess. And that at first I didn't get it, but once you practice it, you'll get it, I guess. I don't fully understand dynamic programming to an extent, but with a bit more practice, it'll go a long way. So first, basic dynamic programming question I'll assign you is longest common subsequence. So this involves being given two sequences. So a sequence is just any string of letters, numbers, or whatever. So, and you're trying to find the longest common subsequence between the two sequences. So a subsequence is just an assortment of letters from a sequence, but it must follow the same order presented in the sequence. So let's say I give you the sequence A, B, C, D, E, F, G. A valid sequence would be B, D, G, A, B, C, D, E, F, D, F, G, B, D, F, or so on and so forth. It just has to follow the same order, and you can take a letter or not take a letter. But C, A, G, or whatever is not a subsequences, it has to still follow order. And a common subsequence is just both. If you take a subsequence from one sequence and another sequence, they have to be exactly the same. And for this question, you won't need to actually find the subsequence itself in the question I assign, but you just need to find the length of the subsequence. But for harder questions, you might have to find the actual subsequence, where you have to backtrack, and that's something we won't cover this year. And there are quite a few concepts you need to know to do the longest common subsequence question. So firstly, the length of a common subsequence between an empty string and another string is always 0, because you can't make a subsequence with an empty string. Secondly, you'll need to check through and check if any pair of letters match. So let's say we're looking at one sequence, we're looping through one sequence, and we're looping through another sequence, all right? And we just have to check, at a given point and another given point at the other sequence, do these letters match? If so, then you have to look at all the letters that you've checked through before and see, have you found a match before, and just add 1 to how many common letters you've found before. And thirdly, you'll need to take the maximum number of the matches before of all the letters you've been searching through and the value you currently know. That sounds a bit complicated, but my important advice is for dynamic programming, you need a pen and paper to do these questions. So it might sound daunting, what I'm explaining, but if you just get bust out a pen and paper, you'll definitely be able to solve these questions. All right. So longest increasing subsequence. So similar to the last question, this question is a bit different now, as you're given only a single sequence of numbers, and what you have to do is find the longest subsequence that is exactly in increasing order. So in order like 1, 2, 2 is not increasing, but 1, 2, 3 is. Also, like the previous question, the question I will assign you will also not have you find the exact subsequence, but just the length of the subsequence. So the concept you need to keep in mind in this question is that you need to keep track of the longest subsequence ending with a given number in the sequence. So first, let's say I give you a number 1, 2, 3, 4, 1, 2, 5, 3, whatever, and so forth. First, you check, okay, what's the longest sequence, common subsequence from 1? What's the longest subsequence of 1, 2, 1, 2, 3, so on and so forth. And you have to go through every number in the sequence, then look back and see if you can add this number to any given subsequence that you already know. And every subsequence had at least one number in it, unless there's no numbers in the original sequence. All right. Those two questions, they're a bit confusing at first. I personally myself had a bit of trouble doing these questions. But this next question I'll be talking about is one of the first dynamic programming questions that I would recommend you to try. This involves a coin, and it's the coin change problem. So this involves being given multiple denominations of coins. So let's say, so here in Canada we have a quarter, we have a nickel, we have a dime. We don't have the penny anymore. Quarter, nickel, dime, loonie, and toonie. All right, those are the coins we have, and you're asked to find the minimum number of coins to make a certain amount of money. So it's like, if I only give you nickels and dimes, or if I give you only dollars and loonie and toonies, how many coins? What's the minimum number of coins that you need to give me to make X amount of money? And you're given unlimited coins as well. So you can have 100 loonies, 200 toonies, or so on and so forth. So there are two basic concepts that you need to understand when solving this type of question. Firstly, it takes 0 coins to make $0 for obvious reasons. You don't have to use any coins to make nothing. No money, I guess. And secondly, the number of coins to make X dollars is either the number of coins that we currently know to make that makes this amount of money, or one more from some other number that we found out before, and depending on what coin we add. So let's say right now it costs us 13 coins to make $50, all right? But I have a $5 coin. Let's say I have a $5 coin, and it takes me 10 coins to make $45. That $13 coins that's more coins than just me adding this one $5 coin to how much it takes me to make $45. And that's an idea that we have to use in coin change. All right. And the final thing we'll be covering is Knapsack. So this is one of the most common and important questions that we will cover in dynamic programming, and I will spend a whole lesson on Knapsack. Since Knapsack, there's a whole detail behind it. There's a lot of details about it. But the general gist, it's like coin change, but rather than trying to minimize something, so minimize the amount of coins to make with a certain amount of money, we're trying to maximize something. And that's what you might commonly see with dynamic programming, is we're either trying to minimize something or maximize something. And this question involves being given a backpack that can only carry a given maximum weight. So let's say I can only carry 20 kilos in my backpack. you're also given a bunch of items with a certain value and a weight, and you need to find the maximum value of items that you can carry, you can put in your backpack. And the concept of this is similar to coin change, where you don't get any value for taking nothing, for obvious reason. Also, the value at a given weight is also it's either the current weight you know of, or, of the item, plus whatever value if you didn't take the weight of this item, or the current value you already know of, taking X amount of weight. And I forgot to include this in the lesson. Most Knapsack questions you can only take an item once, but some questions also allow you to take multiple items. So it depends on the question. Some do unlimited, some do you can only have one item. So concluding with those basic dynamic programming questions, these are just the surface of dynamic programming. There are so many dynamic programming questions out there, and there's so many variations to these questions. You'll also have to come up with your own solution to some of the dynamic programming questions, as there are many ways to approach a dynamic programming question, as well as many types of dynamic programming questions. All right. And that concludes, I guess, today's lesson. Here are all the questions that I assigned for you guys. It might be a lot. A reminder that you don't also have to do the questions in an exact order I present them. Do them in any order. Some of them are more trickier than others. So feel free to do them in any sort of order, I guess. So I would recommend, though, you doing banknotes. As like the first question. That should be my first question. Actually, I should just but I also would recommend doing unlimited numbers, just unlucky numbers, since that covers prefix summary, right? So let me just put banknotes first. Actually, banknotes seems like the better question that I should cover. That you guys should cover first. So I guess these two questions here I would prioritize you guys writing first, but everything else here is all dynamic programming. All right. Does anyone have questions about that? Also, if you guys do manage to finish all the questions and want more dynamic programming review, you will notice that these last things here end with a letter in descending order. So it's like DPA, DPB, DPC, DPD, DPE, DPF, DPG, DPH. This isn't intentional. If you want more review, you just change the last letter of the to the next letter of the alphabet. So DPH, if I go to the link, if I go change this to DPH to DPI, it gives me the next set of next DP question, I guess. DPJ. It also goes up to DPZ. All right. So those are all the DP questions I'll be sending. Does anyone have questions about that? Anything that you want me to recap about?
Could you maybe recap prefix sum arrays?
All right.
Yeah.
So our prefix summary. So let me just draw on whiteboard since I kind of forgot to use my whiteboard here. So let's say we're given that value, the prefix summary again. So this array here, 1, 10, let me move this here, 1, 10, 2, 5, 8, 16, 24, 3, 8. All right. So a prefix summary pretty much just keeps a running total of this array. So deep running total. So let's start off with the running total here. So whoops. You start off with 1, I guess. So that's the first value of this prefix sum. So prefix sum array. Then we have to add 10. So that's the next value. So when we add 10, that would be 11. Then the next value would be 2. So we add 2 to that, the running total, 13. Next value would be 5. So yeah, whoops. It set this to 18. Then from 8, we would add 8, 26. Add 16, that'd be 42. We add 24, that'd be 66. Add 3, that'd be 69. And from there, it'd be 77. All right. So those are the values here. Now, this keeps a running total of all the values in prefix and in the array. All right. Now, with algebra. So let's say we'll assign each of these values here. Like let's say we'll assign them a letter. So like we're given a whoops, I don't know why it wants to keep moving. Whoops, A, B, C, D, E, F, G, H, and I. All right. Let's say we're given those letters, and those are corresponding letters. With algebra, you can see that if we have like this is just A here, so the first letter of the prefix summary would just be A. Second one would be A plus B. Next one would be A plus B plus C. Next one would be A plus B plus C plus D, and so on and so forth, right?
Yeah.
So let's say we want the values. Let's say we want the sum of this value here, these values here, right? Or actually, let me just these values here, right?
Yep.
So we already know the sum of from here all the way to here. We also know the sum from beginning all the way to here, right? If we just do algebra here, so it'd be like in this case it'd be whoops. Why does it want to keep moving on me? Okay, A plus B plus C plus D plus E plus F plus G plus H plus I, right? And then we already know from A to A plus B, A plus B plus C plus D plus E. If we wanted to find the sum of F, G, H, I, we just subtract A plus B plus C plus D plus A plus B plus C plus D plus E, right?
Yeah.
So we can use that same principle with the prefix summary, since we already know each individual value from A all the way to some other value, or like in this case, index 0 to some other value. So we take, okay, in this case, the very last number value. So this would be 0, 1, 2, 3, 4, 5, 6, 7, 8. There's that'd be index 8. So at prefix sum at 8. So prefix sum at 8 would give you this number here, right? This is 8. Now, we also want the prefix sum up to this point, right? So that's the very last value, right?
Yeah.
So that'd be 0, 1, 2, 3, 4. You just subtract prefix sum up 4. And that would get you all the values. It'd get you that would equal sum of array from 5 to 8. And that's kind of what you can do with prefix sum arrays. Does that make sense?
Yeah, I understand it now.
Yeah. So that's what you can do with prefix sum arrays. So rather than having to go through and add this up, we can already, find a sum of all the values starting from 0 to any given value. And then we can just manipulate it from there. We can just manipulate with algebra. All right. Does anyone else have any questions about that? No other questions? All right. If no one else has any questions, I guess we can end it here. If anyone does have any questions, feel free to post in the chat. Ping me because I don't really get every single notification. So if you do have a question, please make sure to ping teachers, I guess. Ping any of the teachers, and whoever sees it first will respond as quick as possible. And if you don't want to, let's say you don't feel comfortable posting a question in the chat, feel free to message me directly. I pretty much check Discord 24/7. So, yep. If no one has questions, any questions now, I guess we can wrap it up today. So, I guess that's our lesson for today. And I hope you guys have a nice day.